Hello, how are you friends? I'm hoping that you are doing good. It's been a while. Welcome back to Bromtech Engineering. Here we learn on how to design structures and how to do construction on site. Today I'm going to take us through the study of the design of strip footing. We are going to see how you decompose the loads from your structure to the strip, and then after you have your loading, then the next thing is how do you design the strip so that you size it properly and you provide the required reinforcement. And we are going to consider a strip footing that is basically which is a slab element that acts like a footing that supports walls, continuous walls, and we are going to look at one which is reinforced. So welcome. Once you want to design your strip footing, first of all you should know where your strip footing is supposed to be designed. Strip footings are normally designed for masonry. They are the ones the loading that comes from masonry is transferred to the foundation through strip footing, similar to the way pad footings transfer the loading of columns to the foundation. So we are going to start from the beginning. First of all, before you start designing, you need to be aware of general considerations that are supposed to be done when designing a strip footing. Number one, general information that you need to have is the first one is the steel yield strength. And this one varies from country to country, but in my country right now, in over the counter or readily in hardware, you will get steel with a yield strength of 500 newtons per millimeter squared. And then for concrete compressive strength, this one you select depending on the class of concrete you want to have. And for these I have decided to use class 20, and in some cases you could use 25 or 30. So for this project I have just decided to use 20. These are the general assumptions you make depending on the magnitude of the project, the kind of load you're dealing with, and workmanship on your site. And if workmanship is poor, sometimes we design with class 20 and then we detail with class 25. But for now we are going to do class 20. And then of course density of concrete, naturally it's 24 kilonewtons per meter cubic. And then the density of masonry varies. You could be having light masonry, dense masonry, and all this is depends on the stones or the bricks you're using for your construction. So in this case, we normally use some stones we call Ndarugo stones. I'm talking about Nairobi, Kenya. And here the density of this masonry, sometimes it varies from 18 to 22 kilonewtons per cubic meter. So in this case, one of the stones that I determined its density in the laboratory was around 19 point something. So I assumed the use of 20 kilonewtons per cubic meter as the density of masonry. And then for your concrete cover of any foundation structures, it is good to always note that foundations are the ones that are susceptible to issues to do with water. If the water has a lot of chlorides or sulfates that are going to attack your concrete, then you need more cover so that it can cover the reinforcement. And that is why we do 50 millimeters. This one actually we design for depending on where you are. But in grounds where we don't have main minerals that attack concrete, and where we don't have salts in groundwater, we normally do 50, and moderate exposure conditions, you could do 40 to 50 millimeters cover. And then the width of my wall is governed by the stone I'm using, and 200 mm is, I've decided it to be the minimum thickness of my wall, so I'm going to use 200 mm thick stones to build this. In determination of the wall height, I have considered the substructure, which is 1.5 meters long high, and then I have 3 meters on the superstructure, and that gives me 4.5 meters or 4500 millimeters as the wall height from the strip to my beam or my ring beam. So here there are very many considerations you could make. Sometimes as we will see in loading, sometimes we want to do load bearing walls, therefore our strips are the ones that are going to bear our loads. So we are going to play around with this height and how we're going to distribute the loads, but we will see that when we get to the second this second row where we're dealing with loading. Now the next thing that is very important to determine before you start designing is the allowable soil bearing capacity. And soil bearing capacity, depending on the magnitude of the project, it's advisable that you carry out the tests in the lab. You can carry out the shear box test or the plate load test on site or any other test to determine the bearing capacity of your soil. This will help you determine the ultimate capacity that your soil can take in, so that you design for that. And this is guided by the British 8004, the 1986 version. Table 1 talks about how you can assume a bearing capacity depending on the soil that you have on site. But in some cases, this is not advisable to select like this. It is good that you carry out the actual test. And I think I'll just open that. Yeah, it's right here. Yes. You see, this is the code for foundation, and it was formerly CP 2004. And this code, it is code 8004 1986. This code is very good. You need to have its information so that it helps you when you're doing design. And then you see it has different sections. Section 1 is generally the definitions. Section 2 talks about all the things that you're going to encounter, including ground movements, groundwater. You have issues to do with flooding, allowable bearing, pressure on various types of grounds, structural considerations, and all these things that you need to take into considerations, including retaining walls. And then for shallow foundations, we also have some notes here. And then deep foundations, we also have a guideline. Cofferdams and caissons, geotechnical processes, including the temporary works that you carry out on site, like dewatering, and pile foundations, tide work, or when you're working underwater. This is majorly in the sea, and diving of as construction is going on, site preparation for foundation work, and all these things. So these will guide you, including safety precautions and all you need on site. But today I want us to look at how to get this allowable bearing pressure on various types of ground. That is page 13. Table 1 is in this page. And then we are also going to look at strip foundation, which is 36. So we start with page 13 first. Let's go, let's look for it. Page 13. There we go. This is 6. You can download this code and be going through it. It can be very, very helpful. Yeah, here it is. So from page 13, we have allowable bearing pressure on various types of grounds. And then you have a lot of information here on how you are going to determine this. But my main consideration was this table: presumed allowable bearing values under static loading. And remember, this is under static loading. So when you have dynamic loading, that will necessitate that you carry out the actual test to determine the bearing capacity. And also for static loading for high rise buildings or very, very high loads, you also, like in bridges, it is expedient that you carry out these tests to find out the ground that you want, where you want to lay your foundation, whether it is able to withstand. So we have different categories here. The category number 1 is rocks, and then you have the presumed allowable bearing value. This is in kilonewtons per square meters, and this is in ton per feet squared. Yes. So so you have for rocks, you have from 10,000 2,000 to 10,000, and these are for very very strong rocks. If you have very high axial loads and they are lying on rocks, these are the ones you consider, but it's always good you test these and find out the actual bearing capacity. Then when dealing with non-cohesive soils, including gravel, sand, and whether dense or loose, you have values from 100 to 600. Now when you're dealing with loose sand, you have a value of less than 100, and this depends on the type of rock, the location, the depth of the water table, and all those other considerations. So assuming you have dense gravel, you could use values greater than 600. If you have loose gravel, you could use values less than 200, and if you have compact sand, you could use values greater than 300. So depending on the type of soil you have on site, you could choose your value. And in this case, the strip that we're designing a strip that we assumed to be in very stiff boulder clay and hard clays. This our structure was in a place with loam soil, and having tested soil in the same locality before, I found out that the soil was predominantly clayey silty. Means there was very little gravel or sand in that soil. Therefore, because it was also very well compact, we considered the use of stiff clays, or very stiff boulder clays and hard clays, because it has a lot of high clayey material. And then here you also have these remarks. Group 3 is susceptible to long-term consolidation settlement, and then you can see this clause of this very code to be able to understand what that means. So from these, the limit is from 300 to 600 for stiff boulder clays, and then for just stiff clays you have 150 to 300. So I assumed bearing capacity of 200, and 200 is what now we will use. But depending on your project location and all these other parameters, table 1, which is in page 15, comes in handy. Also, before we leave here, you note that you have pit and made ground or fields. These are mostly imported soils, and there are ways that you can be able to determine whether the soils are imported or they were existing there before. So we do not do foundations on imported soils unless it is really necessary, and that is when it might require you to think of doing floating foundations or doing piles or any other applicable systems. And then for peat or organic soils, peat are just the soils where we do our farming on. Basically they're the topsoils, and currently according to this code it's not applicable to do foundations here. But with the research and technologies like the use of rammed earth and these technologies we're discovering now as we're doing our research, there are ways in which you can deal with peat if you want to do a foundation on these soils. But it is good you involve a geotechnical engineer so that he is able to guide you on these types of soils. Now let's rush to page 36. Now also you can see the classification and presumed bearing values for high porosity chalk, and you can observe that you have 125 to 250, and the descriptions have been given here. So if you're dealing with rocks with high limestone or chalk, you can use this table also to determine your bearing capacity. And weathering scheme and presumed bearing values for for Cooper Mal, the values are also here, and then you can go through them. Just find your own time, download this code. It is freely online. As you can see, I downloaded it from pdfcoffee.com, so you can get it freely online, and it can guide you on how to design foundations. So now we rush to page 36. See, undrained immediate shear strength for cohesive soils, and then they have been listed here. These are just basically average values that they had obtained over the years. And page 36, we are in 31. 36 is here, shallow foundations, and then selection types of shallow foundations. You see, a pad foundation is used for the purpose of distributing concentrated loads. This is when you're dealing with columns. Then you have issues to do with extensions. Then they have discussed pad. Now we are in strip. In strip, similar considerations to those for pad foundations actually apply, so find time and read this. On sloping sides, strip foundation should be on a horizontal bearing, stepped where necessary to maintain adequate depth. So it is not advisable to have strip foundations that are sloped. It is good that they are on level ground. And if you have if the slope is very high, you can do steps, or you design a house that is has steps, which we normally call a bi-level house. So you could take this into consideration. And then of course I had mentioned about continuous wall foundations. Strip foundations act very well. Wall foundations, in continuous wall foundations, it is recommended that reinforcement should be provided whenever an abrupt change in magnitude of load or variation in ground support occurs. Continuous wall foundations will normally be constructed in mass concrete, provided that the angle of spread of load from the edge of the wall base to the outer edge of the ground bearing does not exceed 1 vertical in 1 horizontal. Foundations on sloping ground and where regrading is likely to take place may require to be designed as retaining walls, so that they are able to accommodate the steps between the adjacent ground floor slabs or the finished ground levels. And you can appreciate this when you have the project on site. Also, at all changes of level and reinforced foundations should be lapped at the steps for a distance of at least equal to the thickness of the foundation, or a minimum of 300 millimeters. Where the height of the step exceeds the thickness of the foundation, special considerations should be taken. So ensure you achieve this lapping that is talked about here whenever you change your level. Also, I would like to note of this: the thickness of reinforced strip foundations should not be less than 150 millimeters. Therefore, if you're planning to reinforce your strip, you have to do a depth of greater than 150, and care should be taken with the excavation levels in order to ensure that this minimum thickness is achieved. And for good construction, you are supposed to normally do some blinding to your ground, so that it provides a good platform to work on. And then now you determine the 150 or design for much higher. Like in our design, we will note that we will design for a higher depth of a strip. Sorry. So you have issues to do with wide strip foundations, trench fields, or deep strip footings, and you can study this. It gives basic guidelines that you're going to use. For instance, here they talk about where the thickness of such a foundation is 500 millimeters or more, any step should be not greater than the concrete thickness, and the lap at such a step should be at least 1 meter or twice the step height, whichever is greater. So these are guidelines that guide you whenever you are sizing these elements and designing them. Basically, this code is very useful whenever you want to design your foundations. And you can see these are deep foundations, and we were just dealing with shallow foundations. Actually, strip footings are normally shallow foundations. So having mentioned this code, therefore we go back to our design. Now you have seen how we obtained this from table 1 of this BS code 8004, which was formerly CP. Which CP was this? Which was formerly CP 2004. The next thing is, first of all, after you've listed down your design information, you now do your loadings. For loadings, we are going to determine the maximum loadings that are going to apply to our service loadings that are applying to our strip footing, and the ultimate loads that are applying to our strip footing. And basically different strip footing support different loads, and I'm going to explain that in a short while. So the first thing we did is a determination of the weight of the wall, and this is done per meter run, so that we are able to find loadings per meter run. So we took the height of the wall multiplied by the thickness, multiplied by 20, which was the density of masonry, multiplied by 1 because it is per meter run. So 4.5 multiplied by 0.2 multiplied by 1 give you the volume, and then 20, which is the density. When you multiply this, it gives you 18 kilonewtons per meter, which is the mass or the loading of the dead loading of the wall on our strip footing. And when you look at this, you realize we have done our wall 1.5 meter substructure, 3 meter superstructure. Now somebody may ask, what if we have a ground beam, or we have a beam that is a ring beam that is loading the wall from the top, like we do in bungalows? Or if you have such, you just subtract their dimensions from this weight, and then you multiply by 24, which is the density of concrete. And sometimes we actually use 25 if the concrete is reinforced, so that you're able to find the loading that element is transferring to the strip. After determining all that, you do the self weight of the base. Now you cannot do the self weight of the base without assuming a perfect size, and this you can perfectly do when you are sizing, when you have experience this sizing. So here we will just do preliminary provision, and from what we have studied, the depth must be greater than 150 because we know our strip is going to be reinforced. So here we decided to do a depth of 200, and then for the width to make sense, we will be able to calculate its minimum thickness. But for now, we have decided to use 600, so that when the wall is at the center, it has 200 on the external edge and 200 on the internal edge. This will enable distribution of the moments and ease to work with. So once you do the self weight of the base, we have assumed these dimensions. You multiply them and multiply by 1 because we are doing this per meter run. It will give you the volume, and then you do multiply by the density of concrete to get 2.88 kilonewtons per meter run. And then you have loading from the ground floor slab. From this type of construction, we did the substructure. We were proposing the substructure, and then you do the ground floor slab, which will cover that section up to where the walls are, and then you will do the superstructure walls on top of the ground floor slab. So here we did a calculation of the ground floor slab loading, and we found it to be 0.72 kilonewtons per meter run, and that is 0.2, which is the width of this wall, because our slab is lying on the wall, which is lying on the which is distributing the load to the strip. And then we have 0.15 thickness. Then we have multiplied by 1 so that we get volume. When you do multiply by 24, you get 0.72 kilonewtons. And then after determining this, now we came and added these loads. From observation, you can realize all these are dead loads. We don't have any live loads here, and this is basically the explanation. This strip was placed in a place where we had a framed structure, so most of the structure's loading was distributed to the foundation via the columns and then to the pad footings. So this our strip was only distributing loads from the ground floor masonry wall to the substructure masonry wall to the strip footing. That is why we don't have any live loads, because if we could be having a load bearing structure where loads from the other floors are distributed to the ground via the walls, then we could determine the live loads, the total live loads from above, and the total dead loads from all the other floors, and we will, the same way we distribute loads to beams, is the same way we are going to distribute loads to this strip, because a strip is basically like a beam or a slab element. So that is how we will distribute the loads. And then we do the dead load, we have added all this, and then we determine the total to be 21.6 kilonewtons per meter. And then for beams is 0 because we didn't have any ground beam. And then when we look at the ring beams, because these are framed structure, the beams are distributing their loads to the columns. So here, if it could be load bearing, then we could get the total loading distributed to the beams here, and then add its dead load and live load here. So in this case, we don't have a live load. Then this being the maximum, you add the total service load, you add these and these to get 21.6 kilonewtons, and the total ultimate load is now obtained by 1.4 dead load, add 1.6 live load as stipulated in the British Standard 8110. And then when you do this, because we don't have a live load, this becomes 0. Then you multiply this by a factor of 1.4, so that you get ultimate load as 30.24 kilonewtons per meter. Let me increase this so that at least it becomes visible. Yeah, so I have been able to determine my service load and my ultimate load. Next is to size my foundation. And to be able to size my foundation, I considered the British Standard 8004 1986. It is just the same, the one we have looked at, clause 3.2.5.2. Let's see, clause 3.2. We are very slow because we want you to understand this. 3.2.5.2. Then you see all this has been considered, and that is why we studied through this, so you now have an understanding of why the thickness was considered to be 200. Yeah. And so to determine the minimum foundation width B, we normally take the service load divided by the net allowable bearing pressure. Ideally, this is not supposed to just give you the minimum foundation width. It is normally width times length. It is supposed to give you the plan area. So the plan area is given by service load divided by the net allowable bearing pressure. And this is how actually we size, we do the initial sizing of pad footings. So when I do this, I find 0.108 meters. But remember, my foundation, I'm designing it per meter run. So I need to get the minimum width multiplied by per meter run. Meter run is 1 meter. So whatever value I'm getting here will be the actual value of B, because this will be this multiplied by 1 gives you the plan area. So when you divide by 1, this is the minimum B that I can achieve together with the service load and the pressure I have in this place. So because I had initially sized 600 millimeters, this is very okay. Also for the depth, from the clause we have read here, the depth must be greater than 150. So the 200 that I had initially sized is also okay. Therefore, we say that we adopt 600 millimeters wide by 200 millimeters deep size of our footing. From there, therefore, you can obtain the self weight of the base as 2.88 kilonewtons per meter run. Basically, the same that was obtained here. Therefore, that shows that we are able to do the initial sizing of our footing well, and it has been able to pass all these tests that we have checked with the British Code. After determining that the size is okay, you now move to determination of the actual pressure that this structure will have on the soil. And the first thing is the determination of the contact pressure. And to get this contact pressure, you normally do service load, you divide it by the adopted footing width. Again, this is not basically just width, it is width multiplied by length, so that this is supposed to be plan area. But since we are designing per meter run, we just do width here because it will be multiplied by 1 to get per plan area. Therefore you do 21.6. This is the service load. Remember, it is not the ultimate load. We have not yet started using the ultimate load. So 21.6 divided by 0.6. The 21.6 was the total service load. And then you divide by 0.6, which is the footing width, to get this value. Next is determine the ultimate. The process is still the same. Q alt is obtained by, now you use the ultimate load once you have factored in 1.4, and because we don't have alive loads, therefore this becomes 0. So you do that divided by the adopted footing width, and then you obtain 50.4 kilonewtons per meter squared. Therefore our contact pressure is 36, but our ultimate bearing pressure is 50.4 kilonewtons per meter squared. From the determination of the actual pressure on the ground, both contact and ultimate, we now proceed to the determination of effective depth. And effective depth, it is the same way we find effective depth in slabs, depending on the reinforcement we're designing and in which direction. So in this case, the first effective depth is obtained by total depth, which is 200. Then you subtract cover from the bottom. This gives you minus 50. And then you subtract reinforcement divided by 2, so that you can go to the center of your reinforcement. And because we are assuming we are using T10s, when you divide by 2 it becomes 5. So 200 subtract 55, you get 145 millimeters. Therefore that is the effective depth of our strip footing. After determination of the effective depth, we now proceed to a different code, which is the British Standard 8110. This is the code of design of concrete. I think we have it somewhere here. Let me open it. Here it is. Structural use of concrete, code of practice for design and construction. Yeah, so it was released in 1997, and this code comes in handy when you're designing concrete structures. We are also going to go through it. You see, this is general information. Basically it's organized like the other code. The other code is for geotechnical purposes, and this is for just concrete design. So you have design objectives and design guidelines. You have them listed there. And then this also talks about loads and material properties. Page 8, I think we can rush there. I want to show you something there. Page 8, this is page 1. So these are definitions, basis of design, robustness. Page 8, wait, 8. This is 7, this is 8. Loads and material properties. This talks about characteristics of value loads, loads during construction, and then material properties. And then you have this is now where we have found 1.4 and 1.6 and the load combination and values for our gamma F for ultimate limit state. And if we could be having wind and earthquake and all these other things, then we could maybe choose this, and you can do 1.2 factor for all. But basically, because this is simple, you see this is 2.4.3.1.1. we can note that here. Where was that? We were doing summation of moments here. This was not noted. So this was the British Standard 8110, part 1 of the 1997 code. And then this is 2.4.3.1.1, 2.4.3.1.1, and then you do table 2.1. Actually, I did this intentionally so that you are able to see how you do references from the code. So that is how you reference them. And then from there you have issues to do with creep and shrinkage and all that information. So this code is very handy. Let's go back to the contents. Then the third section is the design and detailing of reinforced concrete. This is where the most of the work is. This is where most of your formulas are. And then you have design and detailing pre-stressed concrete. This is normal concrete and this is for pre-stressed sections. And then you have design and detailing of precast and composite construction. And then another most important part or section that people normally ignore is these specification and construction materials. This is what will tell you how to strike your formwork, after how many days, how to do curing, how many days, how to treat structural elements and all that. And you have all these other information, including workmanship in terms of laps and jointing, fixing, cutting and bending and welding. And you also have issues to do with pre-stressing tendons. So you see this code is very rich with information. From there, so we go back to our strip design. We are almost done actually, because we have sized our strip, we've determined the effective depth. Therefore we are only going to do design of for the cantilever moment at the free end of the face of the wall. And then we also do shear stress design for that bit. Then we will be done for that section. So the moment is obtained by this formula, where we are now going to start using Q alt, because we use the ultimate moment for design, but we use the service loads for sizing and maybe carrying out serviceability checks. So you do the Q ultimate, multiply into, this is B is the width, subtract the thickness of your wall, and then this is divided by 2 and this is divided by 2. And of course you need to square this and multiply it by Q alt and then divide by 2. And I think here there is a mistake because this is not squared. And I think let's just do that right away. Let's do that. So is it really correct? No, I've not stated it in the correct way. Can state it there. Yes, that is 2, and then you cut that and you place it there. Yes, now it makes sense, now it's true. So this is how you determine the moment. Then once you do this, you are going to get 1.008 kilonewtons per meter run of my strip. Then I also do the ultimate moment of section, so that I'm able to find out what is the ultimate moment of the section that I'm working with. This is 0.15. FCU is the concrete class, then B and D squared. So here it is multiplied by 20 by 10 to the power 3, multiplied by the width of my section, and then I do the effective depth squared, so that I can find the ultimate moment that my section can withstand. Therefore, since the actual moment is less than the ultimate moment, this is thus acceptable. Now because I want to design, I need to determine K, and then I determine lever arm, so that I'm able to use all this information to get the required area of steel. So the formula for K is M over FCU BD squared. And then you can observe all entries have been made here, and this gives you 0.003995, which is less than 0.156, and this communicates something. Once this relationship is achieved, therefore my section does not require compression reinforcement. Once you get K to be greater than 0.156, therefore you provide compression reinforcement for your section. And from this, that means I'm going to adopt this as my K value. So when I feed this value here to determine Z, Z is normally supposed to be equal or less than 0.95D. So when I do this math, I'm going to get a Z of 137.75 millimeters. And just a minute. 0.95 multiplied by D, that is 145. It gives you 137.75. And once you feed the K here, I think you are also going to get a value. So kindly allow me feed the K. Yeah, almost. When I feed this K here, it gives me 0.9955 D. So you see that is greater than 0.95 D. Therefore, we adopt 0.95 D. And then this value of Z is what we are going to use in this area of steel formula, so that we determine the required area of steel. So we use the moment, the actual moment of the section, multiplied by 0.87, and this is the yield strength of steel, and we said it's 500. Can show you, it's right here. And once you multiply by the Z, it gives you 16.82 millimeters squared. Therefore, I can confidently say that we need reinforcement so that it is able to counter this, and this is a very small area of steel required. Therefore, we can provide reinforcement to counter this. So the minimum area of steel for such a section is obtained by 0.13% multiplied by the B. B is the breadth, and then H is the height, and that has been exactly done here to give us 156 millimeters squared. Therefore, since I have to provide reinforcement more than the minimum, I need to provide more than 156. Therefore, I provide the 8 millimeter bars at 200 millimeter spacing, which gives me an area of steel of 252, which is greater than 156, and it's also greater than 16.82. Therefore, this is okay. If you're wondering where I'm obtaining this from, this is the code, and we had looked at it, clause 3.444. This is very useful when you're designing beams, slabs, pad footings, and these strip footings, and even raft. Yeah, it's very, very important when designing beam elements. So we are going to open this code and see these formulas. This is clause 3.4.4.4, 3.8, 3.6, 3.5, 3.45. Yeah, so this is the section 3.4.4.3. yeah, this is the section. For the purposes, these are the symbols that apply, and with these symbols now we have design formula for rectangular beams. You see now K is equals to 0.156 where redistribution does not exceed the 10%. Then of course we have also been given the formula of determination of K, which is right here, M over BD squared FCU, which is exactly this one, M over FCU BD squared, and we have been able to determine our K, and we were told that K prime was 0.156, so our K was less than K prime. That is why compressive reinforcement was not required. And then this is the relationship, compressive reinforcement is not required. So after achieving this, and we have now made sure we don't require this compression reinforcement, now we proceed to design to determine Z, and for Z we use the formula D into 0.5 plus, and then you do all this, which we had done, and we observed that our Z will come into 0.99D. But here we told that this is not supposed to exceed 0.95D. If it exceeds, adopt this. So we adopted this 0.95D. I'm hoping we're following up. So we adopted 0.95D, which is this. I think I can do that. 0.95D. Yeah, now that makes sense. And then from there, the area of steel formula is M over 0.87 FYZ, which is basically this information. But if compression reinforcement is required, therefore we do not use this formula, we use this formula. And what is the difference between these two formulas? You observe that the K we are using here is the K that we basically determined from this formula, this one. But if compression reinforcement is required, we use either 0.156 or we use this formula where redistribution of our reinforcement exceeds 10%. So you can use either this or that. And from there, you now proceed and use the area of steel formula as this one instead of using this one. Yeah, so you have to determine all these parameters and feed them if compression reinforcement is required. And then now this is for flanged beams. Because our strip is not flanged, this is not of concern here. The next thing is shear resistance of beams, but we have not gotten there. Remember, there is one more thing we have not found out where it came from. This, how did we determine that the minimum area of steel is 0.13% of BH? I believe this was from clause 3.12.6.1. Let's see. 3.12. You see now the code, you need to know where what is found. We are now from 3.4, we are looking for 3.12, and we are still within that section. Yeah, minimum areas of reinforcement in members, then minimum percentage of reinforcement in order to control cracking. Then here is our table. This is table 3.25 minimum percentages of reinforcement. And to be faster, we are doing rectangular section in solid slabs. This minimum should be provided in both directions, so which is 0.13. This is what guides us now in the provision of this minimum reinforcement. And you have different conditions and or situations to guide you determine the minimum percentage that you require. And you can observe that if my FY is 250, then I need these ones. If my FY is 500, then I need these ones. Basically, in my country, this one we treat it as the yield strength of the ribbed steel bars, and this is the yield strength of the round steel bars that we normally call R, and these are the ones that we normally call T or D. This is in Kenya, so in your country, if you're not in Kenya, this might be different. So from there, you also have maximum area of reinforcement in members. You have columns, you have beams. Neither the area of tension reinforcement nor the area of compression reinforcement should exceed 4% of the cross-sectional area of concrete. So determine the cross-sectional area of concrete, which is 4%, and then find out this 4% and determine whether these should happen. Just a minute. Let me work on this. Sorry. I hope now you can get me. There was a disruption. You see, where were we? We were talking about 4%. So determine the cross-sectional area and then take your 4%. That should be the maximum cross-sectional area the concrete is supposed to be taking. For columns, it's different, so we are not going to dwell there. And hope you have seen now, you do 0.13 over 100 multiplied by the minimum area by this area of the section to find this. And then when we talk about the shear stress design, this is also found in the British Code. And let me see whether we are still being recorded. Stop. Yeah, it's recording. Then you have this formula. We can go to clause 3.4.5.2. 3.4 wow, right here. So shear stress in beams, the design shear stress V at any closed section should be calculated from this relationship, and in no case should V exceed this or that. So we are going to do this calculation, and this we find the maximum that this V that we can have in this case. So when you look at this, we use the formula 0.8 root FCU exactly, and FCU was 20. This gives you the 3.577 newtons per millimeter squared, or 5 newtons per millimeter squared, whichever is lesser, and that is what the code is communicating here. So to determine now the actual shear force at the face of the wall, you use the formula where you multiply the Q ultimate into breadth divided by 2, breadth of 600 millimeters, and then the width of the wall divided by 2, and this gives you a total of 10.08 kilonewtons per meter run of the strip. And then to determine the actual shear, now you take the V divided by the BD, which we actually carried out here. And then we're able to determine the actual shear to be 0.1159 newtons per millimeter squared, and this value is so small that we are not required to do shear stress design here, because the maximum from our determination was 3.577 newtons per millimeter squared, and here we have 0.1159. Therefore this is way larger than this one. Therefore no shear reinforcement is required for this section. And in most cases, unless you have very high axial loads, then you're not going to do shear design in your strip footings. And next we have longitudinal bending design. Remember, we have designed reinforcement only in the short span. What do we do to get the reinforcement in the long span? When we want to determine the reinforcement in the long span, you have to remember that these strip footings are not suspended, they are laying on bare ground. Therefore, you have to assume that there could be a region that is not well compacted, or there could be a region where reinforcement is required to counter the tension in the strip. Therefore, you assume a local depression occurs on the foundation, and this one will be guided by the type of soil you have, the compaction you're achieving, you're seeking to achieve, and the general layout of your site, because sometimes erosion might occur and the strip might be exposed and such issues. So you assume a local depression, and within this region where we have a local depression, we assume that the strip is now going to behave like a suspended slab, and you design it basically like a suspended, simply supported slab. So first of all, you determine the ultimate load. To determine the ultimate load, you take the total ultimate dead load that we had determined from above, and then you add the backfill load. Where does the backfill load come from? I'm going to show you the end of this. We have this is the sketch of the section we've designed, but we will discuss it later. For now, I want to explain where the backfill comes from. Remember, all the loads we've determined are the loads acting on this masonry. So we also have some soil here, which is a backfill, and it's well compacted, and some soil here. The load of this soil is being transmitted to this strip. So we do this load, add the load of that. This will give you 39.6 kilonewtons per meter run of your strip. Therefore this is the loading you have per meter run of the strip. And then the ultimate moment due to the foundation, you assume certain span of my local depression, and in this case I assumed 1 meter because the ground was well compacted and I didn't see any possibility of erosion or anything that could warrant me to use more than 1 meter. And this you do the moment multiplied by the load by the length squared over 8, and this is basically from theory of structures. You have determined how to do maximum moments for simply supported sections. So this gives you 4.95 kilonewton meters as the moment. And then for effective depth, remember it is now going to be different because this reinforcement will be running on top of the reinforcement you designed above here. So these will be like the bottom ones and these will be like the bottom twos. So the effective depth is determined the same way. The effective depth here is the distance from the surface on the top of the element to the center of the reinforcement you're considering. So here you subtract the bottom cover, subtract the bottom reinforcement, and then subtract half the reinforcement you're considering. So assuming these bars are 10 millimeter bars, then you have 140 millimeter effective depth. And then using this moment, you are then able to determine K from the formula that we highlighted is in the code. I think it is just somewhere right here. Where was that? Here. You determine K and then use the value of K to determine Z. So after determining K and then you find it's less than 0.156, thus you realize there is no compression reinforcement required, and use this value here, and this will give you a certain value. Let me see. Yes, here also this value was greater than 0.95, so we adopt 0.95. If you have a calculator, you can find out what this is by simply replacing this, or we can do it together. 0.0126 divided by 0.9, 0.25 minus answer, then you do the square root, then you add 0.5. This is 0.985D, therefore this is higher, so you adopt this. From that you do the area of steel required the same way, but now we use the moments that we have determined from this case. And in this case, this is not right. We're supposed to have 4.95. 4.95. When you do that math, let's do it together. 10 to the power 6. You have 85.56. This is 85.56 millimeter squared. That is what is required. Then you have minimum area of steel for this section. Remember, now you are considering the 1 meter direction, so you get 260 millimeter squared. Therefore this requires that you provide reinforcement that is going to have a larger area of steel than 260, and these, when you provide 3 T12 bars, you're going to have 339 millimeter squared reinforcement, which is basically greater than 260. Yeah, so this was let me rectify that. 85.56. Then therefore we have design reinforcement for that other direction, and basically because we had determined the shear, we are not going to repeat this again because the section is the same, and we know that now our shear design, we don't need to design for shear reinforcement. So from there, this is the sketch of what we have designed. This is a 50 millimeter blinding. Blinding, we normally use concrete so that you have a clean platform to work from. From this is when you achieve again 50 millimeter cover, and then now you have your reinforcement. And you see we have T8. These are the bar 01 spaced at 200, and they are the bottom 1 bars, the ones running like that. And then we have 3 T12 bars which are coded as 02, and they are spaced basically at not necessarily 200, because if this is 600 and we need to remove cover of 50 and 50 from both sides, then we are going to have a distance of less than 200. So but the maximum should be that 200. And then you have they are the bottom 2 reinforcement, and from observation you can see that we don't have top reinforcement here. But every design and construction situation requires unique consideration. Sometimes you have very high loads that your strip footings are supposed to have top reinforcements either on the entire section, like in sections where they require compression reinforcement, or toward the supports. Remember, this behaves basically like a beam or a slab. So you can tie the top reinforcements towards the support if it calls for and the loads are very high. But all this requires that you design for it. So this basically, this is a section of that footing. Therefore, we have been able to design a footing. Let me take you again through. We listed the design information, we did our loading calculation, and then we sized the footing. Then we determined the actual pressure, both contact and ultimate. And then with the effective depth, we are able to calculate the cantilever moment and find out the reinforcement in this direction. This is the short direction. And we did shear stress design and design for bending. But you can observe that bending reinforcement was more than the reinforcement of that runs in the short span. So most of the times people make the mistake of just detailing this or constructing without design. But from the calculation, you have realized that it is asking for more reinforcement on the longer span and less reinforcement on the shorter span, basically because this is acting like a beam and these ones are behaving like shear links in a beam. Therefore, that completes our study of the strip footing design. And the codes that you need to take into consideration is the British Standard 8004, the 1986 version, and the British Standard 8110 Part 1, the 1997 version that deals with concrete. Therefore, that is where we end our study. Thank you very much for listening and following. We hope that it will help you in the design of strip footings. And sometimes when the loads are very high, you could do a beam on the top so that this looks like an inverted T-beam. And then you can also use the same procedure to design for that. Therefore, thank you very much for you have followed us, you've listened, and now we have designed this. May the good Lord keep you and help you in your design, and continue following us because we are continuing educating you on how to design these elements manually and with the use of design softwares. So actually I will also do this in a design software, and we will also use Excel design sheets so that we can design this and see what is the difference and what is the similarity. Therefore, thank you very much, and thank you for following. Subscribe to this channel, and hope you will learn more. Thank you, and may the good Lord bless and keep you. Adios.